Hello and welcome to lesson 10. So today we're going to be looking at some trigonometry. It's going to be really useful going forward, but we've got a lot to cover today, so we're going to try to get through it as fast as possible while still leaving you guys room to kind of, take it all in, things like that. So the basic trigonometric functions are down here at the bottom. We have sine, cosine, and tangent. So you'll notice that they're both that all three of them, sorry, not both, all three, are equal to fractions with very weird words instead of numbers. So opposite, hypotenuse, adjacent, hypotenuse, opposite, adjacent, opposite, adjacent. Now, if you're not familiar with the trig functions or the geometry that goes into them in general, you might be really confused. Like, what the heck does all that mean? So basically, what a trigonometric function is supposed to do is it's supposed to give you a specific angle based on the triangle it comes from. So let's go ahead and go to the board. So we're over here at the board. So basically, we have this right triangle because every trig function is based on a right triangle of some kind. And actually, you know what? Here, let me get the line tool real quick. There we go. That'll do. So say we have a right triangle. There we go. That's much better. Oh, nope. That was one. There we go. So we got a right triangle here. Like that. Okay, there we go. Lovely, nice little right triangle. So we got a right triangle here, and it's got this angle over here. So the reason I drew that little box right here is this little box means that we have a 90-degree angle. So a right triangle always has a 90-degree angle. And then we've got this angle over here in the bottom right. We're going to call this angle theta. So theta is essentially that angle in degrees. So you can consider theta to just be the degrees for that angle. And for those of you who aren't familiar with what we call radians, so radian is essentially 180 degrees. So if you see fractions like pi over 2, pi over 2 is the same as 90 degrees because it's 180 divided by 2. So 180 divided by 2 would be 90. So that is how we convert the radians, just so you know. So real quick, let's go ahead and erase some of that. Go ahead and erase, what? Where's my, oh. Sorry, I need to fix that. There we go. There we go. Now we're back up to snuff. All right, so we know that theta is just the angle over here on the bottom right side in degrees. So now let's talk about sine, cosine, and tangent. So sine, cosine, and tangent are all based on this theta. So we're going to start with sine. So sine of theta. So what the sine function is supposed to do, because sine is a function, is it is supposed to tell us what the ratio is for the side lengths of this triangle. So what we're going to do is we're going to identify what each side is called. So this diagonal here, the one that's opposite of the 90-degree angle. So if we go opposite of the 90-degree angle, we're going to find this guy. This is called the hypotenuse. Hypotenuse. So the hypotenuse is always the longest side of the triangle. It's always the biggest side. And it's always the diagonal. The diagonal, if we treat, one of the other two sides as the bottom of the triangle, it's always the diagonal. That's called the hypotenuse. And that one, it's pretty easy to find. It never changes. Now, opposite of the theta angle, we have this side called the opposite side. So we call this opposite. And whenever we say opposite, we always mean opposite in reference to theta. So for every single one of these trig functions, we're going to be writing opposite. Opposite always means opposite to theta because we're always doing these trig functions in reference to the angle that we got them from. So in this case, this theta is where we got them from. And so if this one's opposite and that one's hypotenuse, though, the one that's always left over after you have the opposite and the hypotenuse, that one is the adjacent. And the reason it's called adjacent is because it's the side that is touching the theta angle that isn't the hypotenuse. So if it's touching and it's not the hypotenuse, that means it's the adjacent. So we've got our adjacent side right here. So the way this function is supposed to work is sine is supposed to be opposite divided by the hypotenuse. And I'm just going to put HYP for hypotenuse. So hypotenuse hypotenuse right there. So you might have noticed on the other slide we had a big letters we had SOHCAHTOA. So SOHCAHTOA is it's a little mnemonic we use to help us remember how these functions work. So SO means sine is opposite over hypotenuse. So SOH, sine is equal to opposite over hypotenuse. So that one is how we remember sine. Cosine is very similar. So cosine of theta is going to be, so instead of opposite over hypotenuse, so the bottom is still hypotenuse, because, of course, we have the h at the end of it, so therefore the hypotenuse is the bottom of the fraction. So that means the adjacent side, so the ADJ, the adjacent side, is going to be the numerator for cosine. So anytime we have cosine of theta, we're looking at this fraction of the adjacent side over the hypotenuse side. Last but not least, we have TOA. T is for tangent, so tangent is the third function. So tangent is going to be, so we have O and we have A, so it's going to be opposite over adjacent. Now, I know what you might be saying. You're like, okay, so opposite adjacent, I'm supposed to put the thing over thing. Okay, that makes sense, but there's no numbers here. How am I supposed to do this if I don't have any numbers? And you know what? That is a perfectly fair question. So what we're going to do now is we are going to get rid of this degrees stuff, and we are just going to go ahead and give these guys some numbers. So we're going to remove their titles so that they don't have titles anymore. You're just going to have to remember that those are the titles, and don't worry, I'll point them out as we go by, you know, saying, oh, this is the hypotenuse, or, you know, things like that. But you're going to have to remember that we are actually plugging in numbers for these guys. So let's go ahead and move this SOHCAHTOA business. We're going to move this up top. I'm going to make it a little smaller. We're going to move the, I'm going to make it even smaller. There we go. So put that right there. Go ahead and bring this triangle down. So we're going to be working with this triangle. So while we're working with this triangle, we're going to keep theta exactly where it is. So opposite is still over here, adjacent, hypotenuse. So what we're going to do is we're going to make this a 3, 4, 5 triangle. Now you might have noticed the whole time I'm doing this that I never told you what theta was. I didn't tell you what the degrees on this angle are. And that's okay. I don't have to tell you what it is. As long as you know the side lengths, you'll be able to find the fraction values without them. You won't need them whatsoever. So let's say we want to do sine of theta. So sine of theta is going to be equal to the opposite side over the hypotenuse. So the opposite side we know to be 3, and the hypotenuse we know to be 5. So we know that sine of theta is 3 over 5. We can tell that cosine of theta, okay, so cosine of theta is going to be 4 over 5, because 4 is the adjacent and 5 is the hypotenuse. And then last but not least, we have tangent of theta. So tangent, of course, is going to be the opposite over the adjacent. So we know that the opposite is 3, and we know that the adjacent is 4, so 3 over 4. So great. So we did all 3 of these function values. We know what their values are, even though we didn't know what theta was. And that's perfectly okay. You don't always have to know theta in order to work with the trig function. Sometimes you can just look at the triangle and know. With that said, there are a couple of triangles that are really useful because they usually have known values. So what we're going to do now is we're going to talk about 2 different triangles that are very special. We call them special triangles. So if you looked up the special triangles, there's going to be 2 of them. So I'm going to set this one over here. So actually, you know what, we'll go ahead and we'll just do this first. So this triangle, so we're going to use this picture to reference the 30, 60, 90 triangle. So 30, 60, 90 triangles, they're called so because they have a 30-degree angle, they have a 60-degree angle, and of course they have a 90-degree angle. So if this is the case, if this is our setup, then the side lengths will always have the same ratios. So the way this is going to work is this one over here is going to be 1. So this side length is going to be 1. And the longer of the 2 side lengths, that side length is going to be the square root of 3. Now you might be wondering why it's the square root of 3. We'll talk about that here in a second. But we can say for sure that the hypotenuse is going to be 2. So the reason a 30, 60, 90 triangle is so interesting is because, so the shortest side, which is, you know, this guy over here, is always 1, and the hypotenuse is always 2. So according to the Pythagorean theorem, we should be able to square these guys, add them together, and then get the hypotenuse squared. So a squared plus b squared equals c squared. So with that in mind, if we go ahead and do that right here. So 1 times 1, that's going to be 1. Anytime you square square root, the square root just goes away. So 1 plus 3 should equal 2 squared. So 2 squared is 4. So 1 plus 3 equals 4. Great. So really, all you got to do is remember that the short side is 1 and the hypotenuse is 2. And then you can go ahead and solve for the final side if you want to. A lot of people find it easier to just remember. So if you're given, say, for instance, so now let's put this into action, going back to the whole trig business. So let's say, for the purposes of our trig function, let's say someone tells you that, so now if they're giving us the trig function, we are not going to have theta to work with. We're going to have to figure out theta ourselves. Yeah, I know. So earlier we didn't have to deal with theta. Now we do have to deal with theta. I'm so sorry that is... my computer's being a tad naughty right now. It's not doing what I want it to. Be gone, line. Go away. We're not using you anymore. There we go. Okay, so let's say for the sake of instance, or let's say, for instance, that someone asks for sine of 60 degrees. Okay. So normally we had theta over here with a 30-degree angle, but not so anymore. Now, theta is the 60-degree angle. So now we're over here, which means that our opposite side is going to be this guy, because opposite is always opposite of the angle. And they also, we'd still know that this is the hypotenuse. So this is always the hypotenuse, because the hypotenuse is just opposite of the 90-degree angle. So we know that's this is the hypotenuse, this is the opposite, and this is the adjacent. So now that we know that, our angle is 60, we drew the triangle out, we can go ahead and make this work. So it's opposite over hypotenuse. So the opposite is the square root of 3, and the hypotenuse is 2. So there we go. Bing, bang, boom. Square root of 3 over 2. And if someone asked us for tangent of theta, then we could go ahead, or tangent of 60, my apologies. It's very important that it's 60 degrees right now. So 60 degrees, so still the same theta. This is still our theta right here, because it's still 60 degrees. Then we would be able to go, okay, so tangent is opposite over adjacent, so opposite is square root of 3, adjacent is 1. So that means that the tangent is just the square root of 3. And we can also do this in reverse. So let's say that someone decided, okay, we're not going to have any of that information. They're not going to give us a single lick of any of that information. They're just going to go, hey, what is sine of theta? So let's say sine of theta is square root of 3 over 2. Okay, well now it's up to us. Now it's up to us to draw that right triangle, try to figure something out. So there's our right angle. Let's say this is theta. And we could pick either side because this isn't drawn to scale. Obviously, most right triangles don't have a little curve in the middle. That's okay. We're just going to have that for right now. So now we know which side is opposite. We know which side is adjacent. And we know which side is the hypotenuse. So the bottom of a sine fraction, so the value of sine is square root of 3 over 2. So we know that the hypotenuse is on the bottom of the fraction because this is a sine function. So SOHCAHTOA, S-O-H, the H is the one on the bottom, so we know that the hypotenuse is going to be 2. We also know that the opposite is going to be the square root of 3. So we look at this, we go, oh, so 2 square root of 3, that means this guy's got to be 1, because we know this is the 30, 60, 90 triangle. So the thing to remember now is, wait a minute, which one was 30, which one was 60? Oh no, I don't remember. How am I supposed to solve this? Well, so the thing to remember is that the angle is always linked to the side that is opposite of it. So basically, if you open up, this line right here, there's a distance right here. This distance is determined by the angle that's across from it. So if it's a little smaller, it's going to make the side length a little smaller. If I make it a lot bigger, all of a sudden now the side length's got to be bigger. So the bigger angle is always opposite of the bigger side. So the square root of 3 is a little bit bigger than 1. It's not much bigger than 1, but it's a little bit bigger than 1. So we know that this angle has to be the bigger one. So this is the 60-degree angle because we know that this is over here is the 90-degree angle, which means this angle up here is the smaller one. So it's the 30-degree angle. So what is theta? Well, we know that theta is going to have to be 30 degrees, because only this triangle produces these side lengths. You know, if those are the angles involved, that's going to be what the side lengths are. Now, some people are probably thinking to themselves, what have made the triangle twice as big? It is true that if you doubled the sides of the triangle that you would get something bigger. It'd still have that ratio. But we're talking about the lowest possible values. So the lowest possible fraction values are always going to give you these sides for a 30, 60, 90 triangle. So real quick, now that we've got that out of the way, we're going to talk about the other triangles. The other triangle is both easier to remember and a little bit harder in some ways. So the good news is this triangle is really easy to remember because these two angles are the exact same measurement. So this is what we call the 45, 45, 90 triangle. It's called the 45, 45, 90 triangle because these angles are both 45 degrees and this one is 90 degrees. So, you know, we got 180 degrees total, as all triangles do. And so 45, 45, 90, great. So now that means these two sides, the opposite and adjacent, are going to be the same. Wonderful. So here's the part that makes it a little bit weird. So both of these side lengths are 1. And we go, okay, that's fair enough. That's nice and easy to remember. Which means the hypotenuse is going to be the square root of 2. Now you might be wondering, wait a minute. Square root of 2, where did that come from? So what happens here is, so we get 1 square plus 1 square, and that is going to equal the square of our hypotenuse, right? So if we didn't know that this was the square root of 2, we'd go, okay, so this side length is 1, that side length is 1. Okay, so 1 square plus 1 square, so 1 plus 1 is 2. Okay, great. So 1 equals h squared. So now we got to square root both sides. So we square root both sides, and h is the square root of 2. So yeah, it is the square root of 2. So for a 45, 45, 90 triangle, the legs, that is the vertical and horizontal components, are both going to have a side length of 1. And because those are both 1, the hypotenuse is going to be square root of 2. Now, these could be different numbers. If someone gives you a triangle with different numbers, you can still use those to figure these out. And we'll talk about how exactly you'd go about doing that later. But for right now, so let's say someone comes along and they say, okay, well, tell me what we're going on here. Okay, so let's say we got sine of 45 degrees. What the heck is that? Okay, well, so now we need to pick a theta, but oh wait, this is actually really easy because theta could be either 1, it doesn't matter, because opposite and adjacent are both going to be 1. So we're going to put 1 on top of this fraction, and it doesn't really matter which side we would have picked for the opposite or adjacent. But our hypotenuse is always going to be the square root of 2. Now, this is a perfectly fine answer, but a lot of people in the field of math do not like dividing by square roots. So dividing by the square root of 2, a lot of people say, nope, that's a no-go. We're not going to accept that answer. So what we're going to do is to make that answer a little bit easier on people who, don't like radicals inside of fractions, is we're going to multiply by the square root of 2 on the bottom, but we don't want to change the value of this answer. So we're going to multiply by the square root of 2 on top instead. So 1 times the square root of 2, that's just the square root of 2. And if we do square root of 2 times square root of 2, that's just going to give us 2. So this would be our final answer to the original question. So what is the sine of 45? Well, it's the square root of 2 over 2. And so these are the two triangles that you're going to see the most often whenever we talk about sine, cosine, and tangent is going to be the 45, 45, 90 triangle and the 30, 60, 90 triangle that we went over a little bit earlier. And so the last thing I want to talk about real quick before we move forward, onward to the new stuff, is how to build the triangle when you don't know what it looks like. So let's say someone throws you a curveball. So let's say we got sine of theta, and that's equal to, let's say, 4 over 13. And you stop and you go, wait, 4 and 13? I haven't seen those numbers on a sine and cosine yet. What the heck am I supposed to do with that? Well, so what we're going to do is we're going to draw our right triangle, and we're going to decide which side is theta. So let's assume this side is theta. So sine is always opposite over hypotenuse. Again, so opposite over hypotenuse. If we'd had cosine, cosine would be adjacent over hypotenuse. And if we'd had tangent, that'd be TOA. So tangent is opposite over adjacent. So we don't know what this mysterious theta is. But we know that the side length opposite of it has a length of 4. And we know that the hypotenuse is 13. So we can think to ourselves, oh, hey, wait a minute. Now I could use Pythagorean theorem. You know, I could do a square plus b square equals c square. A little bit of algebra, I could figure out what the other side is. And yes, you can. And this is why we like to use these trig functions in order to figure out triangle stuff, because they give us a lot of information even when we're missing certain parts. So I don't know what theta is, but I do know that I can put 4 over here, 13 over there, and I can figure out what that last side length is. So get a lot of information out of these trig functions. And in case you didn't know, the way to help you remember what a trig function does is the word trig is a Greek root meaning triangle. So what does a trig function do? Well, it's a function to help you out with triangles. So if you get lost in the trig function, start drawing triangles. It'll help you out real quick. Okay, so those are the basic sine, cosine, and tangent with the 2 special triangles that make them much more easy to understand. Okay, so we're going to go back to the presentation now. So those are the basic trig functions. Now we're going to jump up to what we call the reciprocal functions. Okay, so the reciprocal functions are pretty much the old functions but flipped upside down. And so what you're going to see is as we go through these, you're going to see that each function that starts with an S goes to one that starts with a C. So that probably doesn't make a whole lot of sense right now. But basically, so cosecant is 1 over sine. So basically, whatever the fraction was for sine, we can flip that upside down. I'll show you that in a second, because instead of opposite over hypotenuse, it's hypotenuse over opposite. Secant goes to 1 over cosine, so that means instead of adjacent over hypotenuse, it's hypotenuse over adjacent. And then cotangent, of course, is 1 over tangent, so instead of opposite over adjacent, it's adjacent over opposite. So that's a lot of words flinging about everywhere. So let's go ahead and let's just start with an example, and we'll start making some triangles, for goodness sake. Okay. So let's say that we have a triangle. And let's say it's one that's nice and easy. Let's say there's a 3, 4, 5 triangle. So if we have a 3, 4, 5 triangle, we say this is theta. Let's start with sine of theta. So sine of theta, as you guys saw with the last one, in this case, sine of theta is going to be 4 over 5, because opposite and hypotenuse. So 4 over 5. So now cosecant, or CSC, is going to be basically be the opposite of this. So instead of the opposite over the hypotenuse, we're going to have the hypotenuse over the opposite. So it's going to be 5 over 4. Then we're going to move on to cosine. So cosine is the next one. Cosine is going to also be straightforward. So cosine, SOHCAHTOA. So cosine is adjacent over hypotenuse. So our adjacent, this case, is 3. Our hypotenuse is 5. So whenever we go over here to secant, so secant of theta. So secant is just cosine, but upside down. So it's going to be 5 over 4. Nice, easy job right there. So instead of adjacent over hypotenuse, we have hypotenuse over adjacent. And last but not least, we have tangent. So tangent, as we pointed out, so it's opposite over adjacent, SOHCAHTOA. This is the TOA part of SOHCA and TOA. So now we're going to put the opposite, which is 4, over the adjacent, which is 3. So then last but not least, we go ahead and do cotangent of theta. And cotangent is just tangent upside down. So instead of opposite over adjacent, we have adjacent over opposite. So that means we're going to go ahead and have 3/4. All right, lovely. So anytime we need to deal with cosecant, secant, and cotangent, just remember that cosecant is sine upside down. Secant, rather, is just cosine upside down. And tangent, or cotangent, is just tangent upside down. So if you need the one on the right, just take the guy on the left, flip it upside down. And there you go. There's your fraction that you need using your angle stuff. Now, we could have done this a little bit backwards. And by a little bit backwards, what I mean is they could have started off by just giving us one of the functions. So let's say they gave us sine of theta. And so just like before, so let's say sine of theta is 4 over 5. So we're going to go ahead and draw the triangle. So we would know that the opposite is 4. So opposite of this angle here is 4. And then we have a hypotenuse of 5. So we can do Pythagorean theorem, a square plus b square equals c squared. And that would eventually tell us that, hey, you know, we do this work with these 3. That tells us that this side would be 3. Now that we know that side is 3, we could do cosine of theta is 3 over 5, and then we could do tangent, and then we could do cosecant, and then we could do secant, and then we could do cotangent. You know, we'd be able to do all 6, even though we only got 1 to start with. And this is another reason why the trig functions are as useful as they are. Is because we're able to get the right triangle from them, we're able to do a lot more work with them than you might initially think, just looking at, you know, a couple of letters and a fraction. So let's go ahead, head back to lecture. And then we're going to talk about, okay, so now we're going to talk about the inverse trig functions. So inverse functions always do the opposite of whatever their function is. So the whole point of an inverse trig function is to take the side lengths and tell you what an angle is. So we're not going to spend as much time on the inverse trig functions, just because I don't believe there's as many of them on your homework. Sometimes they're written as arcsine, sometimes they're written as sine inverse or something like that. I'm going to show you both here in a second. But just be aware that this is mostly for a couple of vector things where you're not given the angle. So that can be useful, but for your immediate future, like that's not going to come up for a while. I'm showing you this more so that when you see it in action in the future, it won't be that strange, because we're already on the topic, so might as well give you a sneak peek. So let's go ahead, switch over. So let's say we have a triangle here. So I'll make this a 3, or a square root of 3. That's the right side. That's a 1, which means that's got to be a 2. Okay, so let's say this theta is here. Now, if you're already ahead of the game, you already know what this angle should be. That's okay. That's perfectly fine. But let's say, for the sake of argument, that we don't. So we got to do arcsine. So let's say arcsine. So arcsine is just sine but backwards. So normally with sine, we'd say sine of theta is equal to opposite over adjacent. So in this case, opposite would be 1. Oh, I'm sorry, opposite over hypotenuse. So opposite would be 1, and hypotenuse would be 2. So sine theta equals 1/2. If you've been keeping up with the special right triangles, you know that this should be 30 degrees. But let's say, for the sake of argument, that you didn't remember that information. So now we know that sine theta equals 1/2, so it's like, oh, well, dang it, I should know what this angle should be, but I don't remember it. So what we're going to do is we're going to put arcsine, oh, that's an A, brain. So we're going to put arcsine onto both sides, and what arcsine does is it cancels out sine. So the sine will cancel out with the arcsine, and we'll be left with theta. So theta is the angle. So this angle is equal to whatever the heck arcsine of 1/2 is. So before, when we were talking about functions, we were talking about functions. So you have the x that you put into it and the y that you get out of it. So normally, when it comes to the trig functions, we put theta into it and we get a fraction out of it. We get something like 4/3, you know, SOHCAHTOA stuff that we've been talking about this whole time. But now what we're doing is we are doing that process in reverse. So now I am giving you the fraction, and you are supposed to tell me what the angle is. Now, in this case, this is something that we can plug into a calculator. So if we plugged arcsine of 1/2 into a calculator, we would be given 30 degrees, or we would be given the radian equivalent, which would be pi over 6. If you do 180 divided by 6, that'll give you 30 degrees. So the radian equivalent would be pi over 6. So with that in mind, this is how the inverse trig functions work. You give them the fraction that you normally get from a trig function, and they will give you the angle that you would normally be plugging into a trig function. Now, again, we're not going to be dwelling on these for too long, but just be aware that just like how we have functions and inverse functions, there are trig functions and there are inverse trig functions, although they're typically written as arcs rather than sine inverse. So instead of sine inverse, you'll see arcsine a lot of times. These two are the same thing. So if you ever see sine to the negative first, that's the same as arcsine. So which is a little unusual. That confuses students sometimes when they see sine to the negative first and it's supposed to be arcsine. This is why arcsine is the name that I've been using this whole time, because arcsine is the one that's slightly less confusing. But just be aware that if you see sine to the negative first and then some stuff's written, this is supposed to be arcsine of whatever that stuff is. Okay, so now that we're done with that, let's go ahead and head back and see what we got next. Okay, so I think that, yeah, so that's going to be the end of our little trigonometry lesson. I know this one was a little long. There's a lot of information to get through, a lot of new ideas you're going to have to kind of sit with and play around with for a bit. Highly recommend go ahead and doing some of the independent practice. Whenever you're seeing this, probably before we come to the synchronous sessions, just because there's a lot of information to go through. Of course, you don't have to. I'm more than happy to explain all of this at the synchronous hours, but just a little thing to help you kind of get ahead of the pack. And of course, there are the Khan Academy videos you can watch to also help you with this. It's just a lot of information. It's a very dense set of topics for this lesson that we're doing right now. So anyway, I will see you next time, and I hope you have an awesome day until then. Bye-bye.